In this section, we're going to talk about antiderivatives. Before we get into the actual math of it, though, I want to talk just for a brief minute about how you reverse an operation that has a series of steps. So let's just take as an example the following rather silly but simple operation: how to put on shoes. So the first step in this process, at least for me, is to put on socks. And then the second step is I actually put on the shoes. And then the third step is then I tie my shoes. Okay, so that's a pretty straightforward set of operations. The entire object here is to put on my shoes and get ready for work. So I first put on socks, then I put on the shoes, and then I tie the shoes. And it obviously wouldn't work out very well if I did these in any different order. If I put on the shoes and then try and put on the socks, it's not going to work. So the order of the operations is important. Okay, now if I want to take off my shoes, at the end of the day, then what do I need to do to reverse these? Well, in addition to undoing each of the operations that I did over here, I tied my shoes, so I need to untie my shoes. I put on the socks, so I need to take off the socks, and I put on the shoes, so I need to take them back off. Well, the order that the operations go in here also matters. The first step is to actually undo the last step. So I need to untie the shoes, and then I need to remove them from my feet, and then finally I might remove my socks. Okay, so you'll notice that each of the operations here is in reverse order from the operations over there. So we might draw this as something like the tie shoes operation went with the untie shoes. The put on the shoes went with the remove the shoes. And then lastly, the put on the socks went with remove the socks. So the order of the operations has been reversed, and in addition to that, each of the operations has individually been reversed. Tying shoes, the opposite of that is untying shoes. When did you tie the shoes? At the end. So when do you untie the shoes? At the beginning. So we've sort of doubly negated each step, if that makes sense. Now, the reason that I wanted to mention this is because mathematically this is exactly what we're going to do. One of the problems that we'd like to know is so let's just take as a quick example. Oops, let me go back to the pen mode. Let's say that I know that the derivative of a function is equal to 4x squared. Now, this is a little backwards from what we've normally said. Normally, I give you guys a function, and then it's your job to figure out what the derivative is. But now we're going to go the opposite direction. I'm going to tell you the derivative, and I want you to tell me what function has that as its derivative. So if we just kind of think about this function for a minute, we might say, okay, what functions have x squared as their derivative? Well, it's going to be something that has an x cubed. When you think about y, what's the derivative of x cubed? 3x squared. Okay, now we need for the coefficients to match up right. So I don't know what this coefficient is, so let me just put in for now. And now if I take the derivative of this, then I get 3nx squared. Now I started with 4x squared. Okay, so what that tells me is that 4 should be the same number as 3n, and hence n is 4/3. So the function that I wanted was 4/3 x cubed. So this function has that as its derivative. Okay, now you may be looking at this and thinking, do I really need to do this sort of sequence of steps? What does this have to do with the shoe thing? And the answer is no, you actually can do a shortcut. So let's think back for just a quick second as to what the power rule said. So if you had a function that was x to the n, then the derivative was n x to the n minus 1. So what did you do? You brought down the power, and then you subtract from the power. Okay, so if we want to reverse this operation, we need to do these two steps in reverse order and reverse them individually. Okay, so the backwards power rule is if you have dy dx is x to the n, then y is x to the n plus 1 over n plus 1. Okay, now why is this the order? Oops, 1 should come first. Why is this the order, and why is that what everything is? Well, the old power rule, the last step was to subtract 1 from the power. So what's the opposite of subtracting 1 from the power? Adding 1 to the power. And because that was our last step before, it should be our first step now. So we need to add to the power. And 2, we then need to not power down. So let's think about what we really did here. We multiplied by the power. Multiply by power. So the opposite of multiplying by the power is to divide by the power. Okay, so we'll look in just a second at another example. Okay, so the next example we'll look at will complicate this just slightly, but not too much. There's one sort of detail that I deliberately swept under the rug in the last example, and that's this fact. Remember that the derivative of any constant is 0. And that's going to have implications for what we're doing. So if we know, say, that the derivative is x squared, then based on what we said before, 1/3 x cubed is a function whose derivative is x squared. But so is any function of this form. Okay, so what this means is that the operation of taking the derivative gives you a unique answer. And doing the opposite process gives you a unique answer with one minor exception, namely this constant. So the way that we typically write this, just for convenience, is something of the form y equals 1/3 x cubed plus constant, and that's a capital C, not a lowercase c. Okay, and that c is just going to represent some unknown constant. It could literally be any constant that you want, and so rather than just picking a constant like 2 or 7 or something and writing it there, we'll just write c to represent that any constant could be there. Now later we'll figure out how you can determine what constant is necessary if you add additional information, but for now we'll just leave it as that's a constant. Okay, so let's go back to what we were doing, and let's work another example. So in this case, let's say that my function is 4x to the 3/5. Okay, now again, let's remember what we're trying to do here. We're trying to sort of undo the operation of differentiation, and in a way then what we're doing is finding antiderivatives. Okay, so it's the opposite of derivatives. So if I wanted to take the derivative of this, I'd multiply by the 3/5 and then I'd take one away from the 3/5. So the process in reverse, I need to add 1 to 3/5, and I'll just come over here on scratch paper and notice that 3/5 plus 1 is 8/5. And so 8/5 is my new power, and then I need to divide by that new power. Okay, now I also need a constant for the same reason that we had it before, and then we could maybe simplify this a little bit. Okay, so what did we do? Derivative, the process is take one away from the power and multiply by the power and then take one away from the power. So this new process goes in reverse. Add 1 to the power and then divide by that new power. Okay, so I added 1 to 3/5 and got 8/5, and then I divided by that right here. Okay, so to simplify this, we're dividing by fractions, so that's the same thing as multiplying by the reciprocal, and that should be a 4 there. And then if you wanted here, we could cancel a 4 here with one of the 4's that's in the 8, and so this would be 5/2 x to the 8/5 plus our mystery constant of integration. Okay, so again, just always go back to the shoe analogy here, that we had to reverse each of the steps for taking the derivative with the power rule and reverse the order in which we applied them. Okay, so I've been deliberately a little vague here as to what this process is called. Now, we have a symbol for what we just did here, okay? And the symbol is going to be the following. So, if I have dy dx equals something, and I want to find y equals something, then the way I'm going to notate this is to say y is this funny looking s symbol dx. Now the reason that I'm doing this is if dy dx is some function, then I can write dy as a differential is f of x dx. And then I can anti-differentiate, and that's what this symbol means, both sides. And then this thing is something that we've learned how to compute, and this thing is just y. Okay, so this symbol here, and I'll tell you guys later what the little S shape is called. So this instruction here just says, find me the antiderivative of f of x. And really it's the antidifferential, but yeah. So find me a function whose derivative is f of x. Okay, so on the next slide we'll look at one more example of this. Okay, so this funny symbol here is called an integral. And in many ways, you can think about it as kind of doing something opposite of what differentiation does. Now, it does a lot more than that, and we'll talk about some of those things next semester. But for now, we'll basically think of this as undoing the operation of taking the derivative. Okay, so let's look at one more example. And this time, the way that the problem is written, it's like this. Okay, so this is asking us to find the antiderivative of the function fifth root of x. Okay? Or another way you could say this is it's asking us to integrate the function the fifth root of x. Okay, so what is this process? First thing we need to do, though, is to rewrite it. And when I say rewrite here, just like with derivatives, if you encountered a fifth root of x, the very first thing you would do is just rewrite the fifth root as x to the 1/5 power. Okay, so that's just the same as what you would have done with differentiation. Okay, now I haven't actually done anything yet other than the rewriting. Okay, once you've got it rewritten in this form, you can actually do the integral. So the derivative of x to the fifth, we'd bring the power down and take 1 away from the power. So the antiderivative, the integral, we need to add 1 to the power, and adding 1 to 1/5 gives me 6/5, and then I need to divide by this new power plus some mystery constant. So the step we just did there was to integrate. And then now let's simplify this a little bit. Instead of dividing by 6/5, I could multiply by 5/6. And so what I've done is rewritten this one more time. Okay, so just sort of a recap here. This symbol is asking me to find which function has the fifth root of x as its derivative. So I rewrote it, did this differentiation process in reverse, and so we'll call that integrating, and then I rewrote my answer. Okay, now let's double check that this is actually correct. One of the easiest ways to check whether or not your answer is correct is just to take the derivative of it again. So if I take the derivative of the answer I got at the end, what I should get is the function I started with. Okay, so integrating and then taking the derivative again, those two operations should roughly cancel each other out, and so I should get this function, the fifth root of x, back. Let's check and make sure that we actually do. So what is the derivative of x to a power? Well, the power, or the coefficient stays put, the power comes down, and I take 1 away from the power. And this constant, the derivative of him, is 0. And then we can simplify. We notice that the 5/6 and the 6/5 cancel. And so I just get x to the 1/5, which is the same as the fifth root of x. So this worked because I got the same function here that I started with. Okay, so one more recap then. We first did this integration operation, rewrite, do something, rewrite again. And then to check it, we just took the old tricks, the old derivative rules, to our supposed answer. Okay, so our answer we thought was this. We weren't sure if it was correct. So I just take the derivative of it, crunch it, see what I get, and I better get the original function. In this case I did, and that means that I've done this process correctly. So in addition, I now know that this answer is correct to the original question. Okay, so we'll talk more about what exactly we're doing and work some more complicated examples in class.